Greetings of the day to all of you. I welcome all to another lecture on pulse width modulation techniques, PWM techniques, which is one of the core courses in your MTech specialization of power electronics and electrical drives. Well, in our last lecture, we discussed bus clamping PWM with unequal device loading. Okay, we injected a second harmonic, common mode voltage with sinusoidal modulating waves MA and MB, and the waveforms got the modified modulating waves modulating waves got modified in such a way that it resulted in bus clamping of a particular leg for 180 degrees. For example, for positive half cycle of inverter output voltage 0 to pi, leg A got clamped to positive DC bus and there was no switching of leg A at all, whereas leg B was switching at switching frequency. In the negative half cycle of inverter output voltage, that's pi to 2 pi, leg B got clamped to positive DC bus and it did not switch at all. So therefore, on the other hand, leg A was switching at the switching frequency. The advantage was that the switching power losses got reduced by almost half, which resulted in increase in the conversion efficiency of the inverter. But the drawback was that only top switches of the two legs, that's TA plus and TB plus, they were on for 180 degrees, whereas bottom switches were not on for this duration of time. So therefore conduction losses were not uniformly distributed among the various devices. In other words, the PWM technique resulted in bus clamping but with unequal device loading. Today we will try to modify the pulse width modulation technique in such a way that it results in bus clamping, because bus clamping has the advantage of reducing the switching power losses, but simultaneously it also results in equal loading of all the four devices of the inverter. So today we are going to discuss bus clamping PWM. I will write here bus clamping pulse width modulation technique, bus clamping PWM with equal device loading. Equal device loading. All the four devices will be equally loaded as far as conduction periods are concerned. Okay, fine. Let me draw the power circuit diagram of inverter, single phase PWM voltage source inverter again. So I am drawing the power circuit diagram of voltage single phase PWM voltage source inverter. So this is the top switch of, this is leg A, load terminal A, load terminal B. Between these load terminals we have a load connected like this, such that the load voltage is V0 and load current may be in either direction and it's I0. So the tops, okay, let's first of all complete the power circuit diagram. These are the DC bus capacitors with midpoint as O. The DC bus voltages, capacitor voltages are VDC by 2 or 0.5 VDC each, and total DC bus voltage is VDC by 2 plus VDC by 2, that is VDC. As far as leg A of the inverter is concerned, its top switch is designated as TA plus and bottom switch is designated as TA minus. For leg B of the inverter, the top switch is designated as TB plus and bottom switch is designated as TB minus. Right. Now in this case, what we will try to do, we will try to go for bus clamping PWM such that each device gets clamped to maybe positive, say upper devices they get clamped to positive DC bus, or the lower devices they get clamped to negative DC bus, but they conduct equally for equal duration of the time, unlike the unequal device loading in which only TA plus and TB plus were conducting for 180 degrees each. Okay, so for that purpose we have to modify our modulating reference wave, because our modulating reference wave, which modulates the switching of leg A, that is MA star, which is equal to actual modulating wave, which is sinusoidal modulating wave like this, plus some common mode voltage. Now in this case, what will be the nature of this common mode voltage, which results in equal device loading along with bus clamping? We have to see. Similarly, the modified modulating wave, which will modulate the switching of leg B, MB star, is actual modulating wave, which is this 180 degrees phase shifted with respect to MA. So if this is MA, this is MB, both are sinusoidally varying modulating reference waves, plus same common mode voltage. The common mode voltage which I have added to MA, same common mode voltage I will add to MB. But this common mode voltage will be such that it will result in bus clamping PWM with equal device loadings. So let us try to derive the modified modulating wave. Okay, for that purpose I have to draw the various waveforms. This is my omega t axis. Okay, first of all I will draw the actual modulating waves, sinusoidal modulating waves, MA and MB. So this is my, for example, MA. Let us suppose the modulation index is 0.8, so its peak value is 0.8 and minus 0.8. So this is my actual modulating wave, MA, or which you call as V control A. It's actual modulating wave. Okay. MB will be 180 degrees out of phase with respect to MA. So let me draw MB, actual sinusoidal reference or modulating wave MB, which is 180 degrees out of phase with respect to MA. So this is my MB. So this is 0, this is pi, and this is 2 pi. It's complete cycle. So this is my actual reference sine wave or sinusoidal modulating wave MA, and this is my actual sinusoidal modulating wave MB. Now what will be the nature of, to this MA and MB I have to add a common mode voltage. What type of common mode voltage will I add such that I get bus clamping with equal device loading? Okay, so this is my, for example, minus 1.0 point, and this is plus 1.0 line. The rule is that in the positive half cycle of inverter output voltage is 0 to pi. Okay, the modulating the common mode voltage. So what type of common mode voltage should be there? The common mode voltage will be calculated by subtracting from minus 1.0 the MB wave. This is MB. Okay, so let me put it this way. Let me first of all take time period 0 to, let me change the pen. Seems that the ink is not there in the pen. So if you take the positive half cycle of inverter output voltage, that is 0 to pi instant, 0 to pi. Now your common mode voltage MCM will have, it will have negative, it will be negative going. I mean, if this is your omega t axis, it will be going, it will be negative, and for some time, and for some time it will be positive. So therefore I can write negative going common mode voltage. Okay, so it will start from negative value and then end up with positive value. So how do you calculate negative going this MCM? This negative going MCM common mode voltage from 0 to pi, it is calculated as minus 1 minus MB. Minus 1 is this, line, -1 line. From this -1 you subtract MB. So this is your MB. Okay, now let us start from here. So from here, if we start, this is -1. As per this formula, it is -1 minus MB. -1 minus MB. What is MB here? 0. So that means -1 minus MB is -1 minus 0. So it will start from here. Then you move ahead. So it will decrease like this. Okay, or it will increase like this. At this point, at peak of MB, actual modulating wave MB, at the peak of MB, which is -0.8, what will be -1 minus MB? It will be -1 minus MB. What is MB at the peak? It is -0.8. So that is -1 minus into minus is plus 0.8. That is -0.2. And where is this -0.2? This is -0.2 line, -0.2. That means if when I go from here to here, near the peak of modulating wave MB, the common mode voltage will have this value, -0.2. So it will go all along down like this. It will go down like this till it reaches -0.5. So you can see it has reached -0.2 near the peak. So let me correct it. I draw it again. So it is something like this. This is the peak. So it should come here. So it will come here. It has come here. So this is my MCM, common mode voltage, MCM, negative going, because it's going through negative half cycle. Okay, now at this point itself, now after this point, what will be MCM? When it goes from negative value to positive value. You see, this is the negative going, and then it will be positive going. I will write here positive going common mode voltage. When it goes from negative value to positive value. This MCM for positive going value is given by 1 minus MA. Now it will be this 1 minus this modulating MA. Now you see near the peak of this MA, okay, what is 1 minus MA? 1 minus, what is peak of this 0.8? 1 minus 0.8. So MCM at the peak of positive, at the peak of MA, it will be 1 minus peak of MA, that is 0.8. That 1 minus 0.8 is plus 0.2, and plus 0.2 is somewhere here. This is 0. Sorry, this is 0. This is not 0.2. 0.2 is somewhere here. Plus 0.2. This is plus 0.2. So it will immediately jump from minus 0.2 to plus 0.2 like this. Okay. Let me draw it again. There is some. First of all, I will go to this. It starts from here. So it is like this, and then it jumps from minus 0.2 to plus 0.2. And then go along this. You can very clearly see now in the positive going, when you consider positive going MCM, it is 1 minus MA. So you can say 1 minus MA, 1 minus MA, 1 minus MA all the way. So it goes, and at pi, what is 1 minus MA? MA is 0. So at omega t equal to pi, MCM is equal to 1 minus MA, that is 1 minus 0, that is equal to 1. That means it will now increase up to 1. So it will increase like this. So ये आपकी common mode voltage है for, from 0 to pi. It is like this, like this. In the negative, when it is negative going, okay, it's calculated by this formula, minus 1 minus MB, minus 1 minus MB. And at the peak of this MB, okay, that is at omega t equal to 90 degrees. This MCM, I have already calculated, and calculating again, is minus 1 minus MB. That is equal to minus 1 minus, what is MB? MB is minus 0.8. Minus 0.8. That is equal to minus 1 plus 0.8. that is minus 0.2. So it goes like this up to 0.2 near the peak of MB. And then it jumps from minus 0.2 to plus 0.2, because when you are going from negative going MCM to positive going MCM, then at this omega t equal to 90 degree itself, MCM for positive going is 1 minus MA. So 1 minus, what is MA? 0.8, that is 0.2. So it jumps from minus 0.2 to plus 0.2, and it increases like this in a sinusoidal manner, but like this. And that at omega t equal to pi, I have written here, MCM is 1 minus MA. 1 minus, what is MA here? 0. 1 minus 0 is 1, so it jumps to 1. Okay, so this is the nature of common mode voltage in the positive half cycle of inverter output voltage 0 to pi. What about pi to 2 pi? Let us see. Pi to 2 pi, that is negative half cycle of inverter output voltage. Pi to 2 pi also, it is again, it will be positive first, negative going and then positive going. So it will jump down, ये नीचे आएगी, ये waveform नीचे आएगी, and then let us see how it changes, how it varies. Okay, so again it is negative going MCM, because when it jumps from, from positive, this is the nature of MCM in the positive half cycle of inverter output voltage 0 to pi. Now in the negative half cycle of inverter output voltage pi to 2 pi, let us see how it looks like. Negative going MCM, पहले negative going होगी, then it will be positive going. Now negative going MCM will be like this. MCM will be minus 1 minus MA. See, in the from 0 to 90 degrees, 0 to pi, negative going MCM was calculated by the formula MCM is equal to minus 1 minus MB. But from pi to 2 pi, the negative going MCM will be calculated by this formula. MCM is equal to minus 1 minus MA. Because now this is minus MA. Okay, so it is minus 1 minus MA. At this point, what is MA? 0, and minus 1 minus 0 is 0, so it will start from here. फिर ये decrease होना, increase होना शुरू हो जाएगी like this. And at peak of MA, that is at MA equal to, say this is 0, 180 degrees, 180 plus 90 is 270 degrees. Peak of MA, negative peak of MA occurs at 270 degrees, because this is 180 degrees, 180 plus 90 is 270 degrees. What is MA? MA का value है minus 0.8. Okay, so therefore as per this formula, what is common mode voltage? It is minus 1 minus MA, that is minus 1 minus MA is 0.8, that is minus 1 plus 0.8, that is minus 0.2. It's minus 0.2. And where is minus 0.2? Point here. This is 0.2. So it will increase like this. And then it's negative going and positive going. I will write now positive going common mode voltage. How will you calculate that positive going common mode voltage? That will be calculated by this formula. MCM is equal to 1 minus MB. 1 minus MB, because MB अब positive हो रहा है. Okay. Now at the peak, what is MB? MB is 0.8. That means at omega t equal to 180 plus 90, that is 270 degrees. MB, you can see MB is 0.8. So therefore, what will be common mode voltage? It will be 1 minus MB, 1 minus 0.8, that is 0.2 plus 0.2. Plus 0.2 ये है. That means it will quickly jump from minus 0.2 to plus 0.2. Right? उसके बाद कैसे vary होगा? उसके बाद it will be 1 minus MB all the way, and at omega t equal to 360 degrees or 2 pi. What is MB? You can see at MB is 0. So therefore MCM, which is equal to 1 minus MB, is 1 minus 0, that is 1. So ये ऐसे rise होगा. So ये आपकी common mode voltage है. So this is your common mode voltage. Okay. In our last class, when we were discussing, our common mode voltage was like this. आपकी common mode voltage, अगर आपको याद हो, ये 1 था, it was like this. ये आपकी common mode voltage थी 0 to pi and pi to 2 pi. The second harmonic wave. But in this case, the common mode voltage is not like that. The common mode voltage is like this. It increases sinusoidally, jumps from minus 0.2 to plus 0.2. Then again, it varies sinusoidally up to pi. Then from pi to 2 pi, it first increases sinusoidally, then jumps from minus 0.2 to plus 0.2, then it again varies sinusoidally like this. This is in one cycle and it will repeat in subsequent cycles. Fine. Yeah, so this is our common mode voltage, MCM. Now, what will be our MA star? MA star will be MA actual modulating wave plus MCM. Similarly, MB star, the modified modulating wave, will be actual modulating wave plus this common mode voltage. Let us calculate MA star and MB star. Now, MA star is MCM, ये मेरी MCM है, plus MA, ये मेरी MA. See, this is my MA. You have to add MCM to it, so I will get MA star. Okay. So for example, at omega t equal to 90 degrees, आपकी MCM कितनी है? MCM है minus 0.2 और आपका MA कितना है? 0.8 है. So what is 0.8 minus 0.2? 0.8 minus 0.2 is 0.6. Okay. So that means 0.6 ये है, ये आपका 0.6 point है. This is 0.6. So that means अगर मैं, if I draw this modulating wave, modified modulating wave, आप ऐसा कर ले, MA star is MA plus MCM. So this is your MA, go 0 to 90 degrees. This is your MA, this is MCM, this is MCM, this plus this, okay, MA plus MCM. So it will start from here, okay, and then as you move along, this is increasing and this is decreasing, okay. So this minus this plus this, this plus this, this plus this, this plus this. So it will rise like this in this way. And at this point, what is MCM? It is minus 0.2, and what is MA? MA is 0.8. 0.8 minus 0.2 is 0.6. So ये यहाँ आ जाएगा. So it will increase in this fashion like this. I will use blue color pen for this. ये आपकी modulating. This is your modified modulating wave, MA star. Okay, what is MA star? It's MA plus MCM. So you do like this. अच्छा, उसके बाद from 90 to 180 degrees, you can see MA star is again, it is MA plus MCM. MA आपका 0.8 है और MCM इस point पे क्या है? 0.2. What is 0.8 plus 0.2? 0.8 plus 0.2 is 1. That means it will jump to 1. और फिर from 90 to 180 degrees, if you add MA and MCM, this is MA. MA is decreasing sinusoidally and MCM is increasing sinusoidally. And at this point, MA is 0, MCM is 1, and it means it will get clamped to 1. So it will be all throughout 1 only. Okay. So therefore, from 0 to 90 degrees and 90 degrees to 180 degrees in the positive half cycle of inverter output voltage, this is your MA star, modified modulating wave or modified reference wave, which is MA plus MCM. MA plus MCM, and then 0 to 90 degrees, it increases like this. 90 to 180 degrees, MA star is MA plus MCM. ये आपका MA है, ये MCM है. The sum of the two is always equal to 1. For example, here it is 0.8. It is MA is 0.8 and MCM is 0.2. 0.8 plus 0.2 is 1. So it will jump to 1. From this to this point onwards, it will remain 1. You can see MA plus MCM, it is 1. This is the nature of modulating wave in the positive half cycle, MA star. What about negative half cycle? It will come down. Negative half cycle may be MA star is MA plus MCM. MA आपकी ये है, and this is your MCM. Okay, this is MA ये है, and this is MCM. So this plus this is minus 1 plus 0 minus 1. उसके बाद आप इन दोनों को ऐड कर लीजिए. You just add them up. Okay, when you add them up, it will get clamped to, for example, at this point, what is MA? MA is minus 0.8. And what is MCM? MCM is minus 0.2. So the sum of the two is minus 0.8 minus 0.2, that is minus 1. And similarly, from this point to this point, this plus this, it will all the through be equal to minus 0.1. Minus 1.0. तो ये minus 1.0 के बराबर हो जाएगी. उसके बाद आप This is from 180 degrees to 270 degrees. 270 degrees to 360 degrees. It will be again MA plus MCM. अब ये आपकी ऊपर jump करेगी. It will jump above. ये ऊपर जाएगी. MA is minus 0.8 and what is MCM? MCM is 0.2. What is minus 0.8 plus 0.2? That is minus 0.6. और minus 0.6 ये minus 0.8 है. Minus 0.6 is somewhere here. This is minus 0.6. That means ये waveform अब jump करेगी to minus 0.6. ये minus 0.6 पे आ गई. उसके बाद this is MA. Sorry, this is MCM. We know this is MCM plus MA. इन दोनों को add करो. So it will increase in a sinusoidal manner like this. For example, at omega t equal to 2 pi, what is MA? MA is 0, MCM is 1. So यहाँ पे ये 1 पे जाएगी and it will rise like this till it reaches 1. Okay, so this is my MA star like this, like this. ये मेरी modified modulating way MA star है. What about MB star? In a similar way, I have to find MB star. What is MB star? MB star is MB plus MCM. अब आप 0 to 90 degree देखिए. MB is, this is your MB and this is MCM. तो यही है. At omega t equal to 0, it is minus 1 plus 0 minus 1. फिर आप 0 to 90 degree जाए. For example, when you come to 90 degrees, MB is minus 0.8 and what is MCM? Minus 0.2. Minus 0.8 minus 0.2 is minus 1. और यहाँ से यहाँ तक ये दोनों add हो जाएंगे till 90 degrees and MB star will be, it will remain equal to minus 1.0 all throughout. Throughout it will remain minus 1. उसके बाद from 90 to 180 degrees, it is MCM plus MB. अब आप देख सकते हैं MCM jumps from minus 0.2 to plus 0.2 और MB ऐसे जा रहा है. At this point, your what is MB plus MCM? MB is minus 0.8, MCM is plus 0.2. What is minus 0.8 plus 0.2? That is minus 0.6. That means it will come down to minus 0.6. ये minus 0.6. उसके बाद this plus this till omega t is equal to pi. At omega t equal to pi, MCM is 1 and MB is 0. So 1 plus 0 is 1. So ये ऐसे rise हो जाएगा. It will rise like this. Sorry. It will rise like this. तो ये red color की जो waveform है, ये मेरी MB star है. Okay. And then it will come down. It will come down. मैं इसको dotted दिखाऊंगा. It will come down along this line. Okay. Then from 180 degrees to 270 degrees, it's again MB star is MB plus MCM. ये आपकी MB है positive और ये MCM है. For example, at omega t equal to 270 degrees, what is MB? MB is 0.8 and MCM is minus 0.2. What is 0.8 minus 0.2? That is plus 0.6. इसका मतलब ये ऐसे अब rise हो जाएगी till it reaches minus 0.6. Minus 0.6 पे आ जाएगी यहाँ at this point. उसके बाद MB plus MCM, you can see MB MCM add हो जाएंगे. For example, यहाँ पे how much is MB? MB is 0.8. How much is MCM? MCM is 0.2. 0.8 plus 0.2 is 1. So it will jump to 1. उसके बाद this plus this, that's MB plus MCM, which is MB star, it will remain 1. For example, at omega t equal to 2 pi, MA is 0, MCM is 1, so 1 plus 0 is 1. So ये clamp हो जाएगी to 1. So this is my blue color waveform is modified modulating wave MA star, which is MA plus MCM. It is like this. And my red color waveform is modified modulating wave for leg B, that's MB star, which is MB plus MCM. And we already know that our inverter output pole voltages, VAO and VBO, they will very closely follow the modulating waves. Okay, they will follow the modulating waves. Because when we were discussing single phase PWM voltage source inverter, bipolar PWM or unipolar PWM, there if our modulating signal was MA and our another modulating signal, for example, in unipolar PWM was MB, our pole voltages average Instantaneous average value of pole voltages were also varying sinusoidally. This was VAO and this was VBO. That means the nature of modulating waves determines the nature of average instantaneous pole voltages. But what are we doing now? We are modifying our modulating waves. Our modulating waves are no longer sinusoidal like this, MA and MB. They are like this. This is my MA star. It's no longer sinusoidal. And this is my MB star. So my pole voltages will also be like this. For example, अगर आप pole voltages draw करेंगे, instantaneous average pole voltages. Your instantaneous average pole voltage will be like this. I mean, this will be VAO. It will look like this. It will be, it will follow MA star. So it will follow very closely MA star. And what about pole voltage VBO? What is pole voltage? That will follow MB star. और आपकी MB star ये है. यह आपकी MB star है. It will follow. You can see this is MB star. It will very closely follow it, and then it will come down. It will follow it like this. So this is pole voltage VBO, which will very closely follow MB star. Okay. So now it is very interesting to see that the pole voltages get modified. They are no longer the instantaneous average value of pole voltage VAO is like this. From 0 to 90 degrees, it varies almost sinusoidally like this. And from 90 to 180 degrees, it is equal to plus VDC by 2. Similarly, pole in the negative half cycle, it is minus VDC by 2, and then it's like this. Its average value is like this. Pole voltage VBO, it's minus VDC by 2, and then it varies sinusoidally like this, and then it is plus VDC by 2. Right? So therefore, if you take, for example, let us take various carrier waves. Let us take carrier wave 1, 2, 3, 4, 5. Let me take 6. I'm starting from here. 1, 2, 3, 4, 5, 6. So this is 0 and this is pi. Okay. So how is my modulating wave MA star looking like? So this is pi by 2 is somewhere here. 1, 2, 3. ये pi by 2 है. This is pi by 2. From 0 to pi by 2, this is my modulating wave. मेरी modulating wave ऐसे जा रही है. Let me draw it by blue pen, blue color. It's going like this. Like this. ऐसे उसके बाद ये clamp हो रही है. And 90 to 180 degrees ये फिर its amplitude is same as carrier wave. Okay, because it is 1, carrier wave is also 1. This is VTRI, carrier wave voltage, and this is MA star. So from 0 to 90 degrees, it increases sinusoidally like this, and 90 to 180 degrees, its amplitude is same as VTRI, 1. Okay. And what about MB star? ये मेरी MB star है. MB star 0 to 90 degrees, its amplitude is minus. This is MB star. It's minus 1, and then it increases sinusoidally like this. Okay. So यहाँ से अगर आप pole voltages, if you draw the pole voltages, okay. Where should I draw the pole voltages? I don't have space. Okay, I may need to shift it upwards. What I will do, I will draw it somewhere here. I will draw it somewhere here. I have to look for the space. Wait for a moment. Let me draw it here. Because I don't have space here. I may have to draw it here. HRT axis. Let me take Let me take 6 cycles. 1, 2, 3, 4, 5, 6. 1, 2, 3. So this is 0. This is pi by 2, 4, 5, 6. And this is pi by 2 and this is pi. Okay, I will again draw, MA star from 0 to 90 degrees. It's like this. It's like this. And then its amplitude is same as carrier wave. And what about MB star? MB star from 0 to 90 degrees, it's like this. And then it goes down and goes like this. So this is my MA star. And this red color waveform is MB star. And we know the pole voltages use the logic. How do you get the pole voltages? Let's try to draw the pole voltages, various pole voltages. Let me draw VAO. And for that purpose, I will draw the inverter power circuit diagram again. And I have to reproduce inverter power circuit diagram. Please bear with me, needs some patience. So this is my single phase PWM voltage source inverter power circuit diagram. This is TA plus, TA minus, switch TB plus and TB minus. This is A, this is B, and this is load. Load voltage is V0 and load current may be in either direction as I0. And this is my DC bus. DC bus capacitor voltages are VDC by 2 each. VDC by 2 and VDC by 2, and total DC bus voltage is VDC. Fine. Now, the logic is whenever modulating reference wave is higher in amplitude than triangular carrier wave, okay, the top switch of leg A is on, otherwise bottom switch of leg A is on. Let us see from this instant to this instant. From this instant, let me first of all draw all these projections, these points of intersections. Now from this instant to this instant, triangular carrier wave is higher in amplitude than reference sine wave MA star. Okay, so bottom switch of leg A is on, TA minus is on, which makes VAO equal to minus VDC by 2. So VAO is minus VDC by 2. From this instant to this instant, MA star, that's reference wave, modified reference wave or modified modulating wave, MA star is higher in amplitude than triangular carrier wave, so it will make top switch on. TA plus will be on and VAO will be plus VDC by 2. So it is plus VDC by 2. And then it will again go to minus VDC by 2, then again plus VDC by 2, minus VDC by 2 up to this point. And then from this point onwards, you can see MA star is greater than triangular carrier wave. And for this entire negative half cycle, for this entire quarter wave, that is pi by 2 to pi, 90 to 180 degrees, MA star is higher in amplitude than triangular carrier wave. So TA plus will be on for entire 90 degrees. The 90 say 180 degree for 90 degrees, TA plus will be on, and when TA plus, top switch TA plus is on, what is VAO? It will be plus VDC by 2, plus VDC by 2. Okay, so it will remain plus VDC by 2 for entire, that means from 90 degrees to 180 degrees. This is 0 degree. This is pole voltage VAO. What about pole voltage VBO? Let me draw pole voltage VBO. For VBO, you have to see the comparison between modified modulating wave MB star with triangular carrier wave. So you can see from 0 to 90 degrees. ये 0 है और ये 90 degrees है. MB star is, MB star is -1. Okay, so it is lower in amplitude, it's smaller in amplitude than triangular carrier wave all throughout. And when it is smaller in amplitude, or in other words, from this point to this point, 0 to 90 degrees, triangular carrier waves are having higher amplitude than modulating wave and B star. So for phase leg, for leg B, bottom switch TB minus will be on. And when TB minus is on, what is VBO? From 0 degree to 90 degrees, VBO will be minus VDC by 2. So yeah, all throughout minus VDC by 2, right? And then there will be switching of this leg from 90 to 180 degrees. Here 90 degree hai aur ye 180 degrees. Now we can see from 90 to 180 degrees. यहाँ से हम शुरू करते हैं from this instant to this instant. इस instant से इस instant तक. Triangular carrier wave is MB star is higher in amplitude than triangular carrier wave. So top switch TB plus is on and VBO is plus VDC by 2. यहाँ से यहाँ तक it will be plus VDC by 2. Okay, and then from this instant to this instant, let me first of all draw these projections. That will make it easy to draw. Easy हो जाएगा. So this projection, and finally this projection. From this instant to this instant, triangular carrier wave is higher in amplitude than MB star. So bottom switch TB minus is again on. So it will be minus VDC by 2, then it will be plus VDC by 2. Okay, minus VDC by 2, plus VDC by 2, minus VDC by 2, plus VDC by 2. This is how switching occurs. Okay. So therefore, what is my load voltage? V0. V0 is same as VAB. This is load voltage VAB, which is the difference of pole voltages VAO minus VBO. Let us draw this V0. Okay. So now we can see from this instant to this instant. Then first of all, let us draw all these projections. This instant, this instant, this instant, then this is next. Now you can see from 0 to 90 degrees. This is 0 degree and this is 90 degrees and this is 180 degrees. From 0 to 90 degrees, your V0 is VAB is VAO minus VBO. From this instant to this instant, VAO is minus VDC by 2. VBO is also minus VDC by 2. So VAB or V0 is equal to VAO minus VBO. That is minus VDC by 2 minus plus VDC. Minus VDC by 2 minus VDC by 2. That is minus VDC by 2 plus VDC by 2. It is 0. And what is the pair of switches which is conducting? By the way, when VAO is minus VDC by 2, the bottom switch TA minus is on during this period. And when VBO is also minus VDC by 2, bottom switch TB minus is on. So that means during this period, inverter output voltage V0 is 0 and bottom switches of both the legs, that is TA minus and TB minus, are on. And then from this instant to this instant, top switch, VAO is plus VDC by 2. That means top switch TA plus is on. During this period, top switch is on. Okay. So VAO is plus VDC by 2, VBO is minus VDC by 2. So V0 is VAO minus VBO. That is VDC by 2 minus VDC by 2. That is plus VDC. So ये मेरी VO है, VDC. And what is the pair of switches which is conducting during this period? TA plus and TB minus. TA plus, TB minus. And then from this instant to this instant, it is again minus VDC by 2, minus VDC by 2, again 0. And again TA minus, TB minus switches are on. And then again plus VDC, then again 0. then okay, then again 0, that's it. So this is what happens in the positive half cycle. Right? Now in the from 0 to 90 degrees, from 90 to 180 degrees, अब यहाँ देख सकते हैं यहाँ से यहाँ तक it is 0, this is VAO is plus VDC by 2, that means upper switch TA plus is on, और यहाँ it is plus VDC by 2, that means TB plus is on. During this period, output voltages, pole voltage VAO is plus VDC by 2, VBO is also plus VDC by 2. So load voltage is plus VDC by 2, plus VDC by 2, it is 0. Plus VDC by 2 minus VDC by 2, it is 0. And what is the pair of switches which is now conducting? TA plus and TB plus. And then from this instant to this instant, your load voltages VAO minus VBO, that is VDC by 2 minus VDC by 2, that is again plus VDC, and then again 0, VDC, 0, VDC, 0. So this is the nature of inverter output voltage, VAO. Okay, so before I discuss it with you, now you can very clearly see this is your MA star. MA star from 0 to 90 degrees rises like this, almost sinusoidally, and then it is constant, equal to 1. Similarly, MB star from 0 to 90 degrees, it's constant, equal to 1, and then from 90 to 180 degrees, it varies in a sinusoidal manner like this. I told you a few moments back that pole voltages also follow the same pattern. Pole voltages will have same average instantaneous value as the modulating waves. Now MA star will determine VAO. Now you can see VAO rises like this. So अगर आप in voltage pulses की average value निकालोगे in every carrier cycle, so average value will be like this. You can see it. It will increase somewhat like this. During this, in this carrier period, average value is negative. Then as you move ahead, it will become positive and it will vary in a sinusoidal manner like this. और उसके बाद you can see TA plus is on, your pole voltage is plus VDC by 2 all through. So इसका nature इसके nature के साथ पूरा मिलता है. It is like this. MA star is like this. Your instantaneous average value of pole voltage VAO also varies in this. What about MB star? MB star will determine instantaneous pole voltage VB naught. Instantaneous average value of pole voltage VB naught. It is constant here. It's constant here also. So this will be your VB naught, constant. And then it varies sinusoidally like this. आप देख सकते हैं ये भी sinusoidally ऐसे vary करेगा. तो vary sinusoidally. First it will be negative और उसके बाद ये positive हो जाएगा. अगर आप हर switching cycle में, carrier cycle में instantaneous average value निकालेंगे. So that means whatever is the nature of MA star and MB star, that is modulating waves, same will be the nature of instantaneous average value of load voltage, this pole voltages VAO and VBO. Okay, fine. Now we can very interestingly see that in positive half cycle, I will write here positive. Let us first of all take positive half cycle of load voltage V naught, that is 0 to 180 degrees. पहले हम what we will do, we will take 0 to, shall we take 0 to 180 degrees or 0 to 90 degrees? 0 to 180 degrees, उसमें हम दो intervals लेंगे, 0 to 90 and 90 to 180 degrees. Let us first of all take 0 to 90 degrees interval. This interval will take 0 to 90 degree. In this 0 to 90 degree interval, MB star is 1, minus 1. So that you can see VBO is minus VDC by 2 all throughout 0 to 90 degrees, because MB star equal to minus 1 means TB minus is on for entire negative half cycle, for entire 0 to 90 degrees. So I will write here, during this period MB star is equal to minus 1, which means TB minus phase leg, leg B ka bottom switch TB minus is conducting, or it is on. it's on for entire negative half cycle. So it is on means it is not switching. इसकी switching नहीं हो रही है, ये continuously on है, it's continuously on. Whereas you can see leg A की switching हो रही है, leg B की, so this means leg B is clamped to minus VDC by 2, or it is clamped to negative DC bus. It's clamped to negative DC bus. Since bottom switch of leg B is on, so that means VBO is minus VDC by 2. That means leg B is clamped to negative DC bus, and VBO for whole period is equal to minus VDC by 2. So B is clamped to negative DC bus. Okay. Whereas during this period, you can see A is switching because MA star is not equal to minus 1. It is increasing sinusoidally. So we can say leg A is switching. Leg B switch nahi ho rahi hai. Leg B is clamped to negative DC bus because MB is minus 1, MB star is minus 1, which makes TB minus bottom switch of leg B on for entire 90-degree period. It's not switching. So leg B is not switching. It's clamped to negative DC bus, but leg A is switching because you can see leg A is, leg B switch nahi ho rahi hai. VBO is minus VDC by 2, but leg A switch ho rahi hai, like you can see minus VDC by 2 plus VDC minus VDC. And when leg A is switching, so your load voltage will have, first you can say, first your load voltage has 0 in. When it is 0, you have very clearly seen the bottom switch of leg A, that is TA minus, and bottom switch of leg B, TB minus are on. TA minus, TB minus, both are on. So that makes load voltage V0 equal to 0. So V0 equal to 0. Then what is V0? Load voltage. It is VDC. So load voltage is equal to VDC. When it is equal to VDC, the top switch TA plus of leg A is on, and bottom switch TB minus ये तो throughout 90 degrees on है. So TA plus TB minus on. You can see in the power circuit diagram when TA plus is on and TB minus is on, A is connected to positive DC bus, B to negative DC bus. So VAB or load voltage is plus VDC. And then it is again 0. When it is again 0, then again TA minus TB minus is on. TA minus TB minus on. You can see TA minus on. That makes VAO minus VDC by 2, and TB minus to on hai throughout 90 degrees. So then it will repeat. Okay, this is what happens from 0 to 90 degrees. Let us now see what happens from 90 to 180. So we can say that from 0 to 90 degrees, leg B is clamped to negative DC bus and TB minus is on. So हम यहाँ पे कहीं पे लिख सकते हैं that during this period TB minus is on 0 to 90 degrees. I will put it within the box. I will write it here. 0 to 90 degrees में क्या होता है? TB minus is on. It is conducting. Okay, let us now see what happens 90 to 180 degrees. 90 degrees to 180 degrees. 90 degree to 180 degree में आप देख सकते हैं, you can very clearly see MA star is equal to plus 1. MA star equal to plus 1, which means when MA star is plus 1, which means TA plus is all throughout on. The top switch of leg A is on. TA plus is on during this entire 90 degree interval, 90 to 180 degree. When TA plus is on, what is VAO? VAO is plus VDC by 2. You can see VAO is plus VDC by 2. That means leg A is not conducting, leg A is not switching. TA plus from 90 to 180 degrees is continuously on, which makes VAO equal to plus VDC by 2. That means leg A is clamped to positive DC bus. Leg A is clamped to positive DC bus. So it's not switching. Leg A is not switching at all. Leg A का top switch on है, continuously on है. It's not switching. Whereas you can see leg B is switching. क्योंकि leg B की modulating wave जो है MB star, it's like this. और आप यहाँ clearly देख सकते हैं leg B when it is switching, it produces the pole voltage VBO like this, plus VDC by 2 minus VDC by 2, then again plus VDC by 2 minus VDC by 2. So leg B is switching. So I will write here, leg B is switching. Okay. So leg A is not switching, but leg B is switching. So therefore our inverter output voltage, we can see during this period, it is either equal to plus VDC. You can see it is VDC. When it is equal to VDC, the top switch TA plus is top switch तो throughout 90 degree interval on है, और आप यहाँ देख सकते हैं during this interval the bottom switch TB minus of leg B is on, which makes pole voltage VBO minus VDC by 2. Okay, so the top switch TA plus of leg A and bottom switch TB minus of leg B is on. So TA plus TB minus on. So when top switch of leg A and bottom switch of leg B is on, so load voltage is VDC. Okay. उसके बाद load voltage 0 हो जाती है, then it is 0. It is 0 because top switch तो leg A का on ही है, bottom switch भी top switch leg A का on है, leg B का भी top switch on हो रहा है, क्योंकि during this period the top switch TB plus of leg B ये on हो रहा है, that's why इसकी pole voltage plus VDC हो रही है, plus VDC by 2 हो रही है. So therefore during this interval, during this 0 voltage interval, the top switch of both the legs are on. TA plus तो on है ही, TB plus भी on हो रहा है. Okay, earlier TB minus was on, lower switch of leg B was on, now top switch of leg B is on. So there इनमें switching हो रही है. Okay, then your load voltage is again VDC. It is again VDC because TA plus TB plus are again on. You can see TA plus is on all throughout. Okay, इसकी switching नहीं हो रही है, लेकिन TB की switching हो रही है. I mean leg B की switching हो रही है. So first TB minus is on, then TB plus. Then again it was TB minus, again on. Then it will be again TB plus. So leg B is switching. Okay, so therefore from 90 to 180 degrees, 90 to 180 degrees में कौन सा switch permanently on है? Yes, TA plus is on. Leg A is clamped to positive DC bus. इसका switch, top switch TA plus is permanently on. Okay, so I will write here. I had previously written 0 to 90 degrees. TB minus is on. Bottom switch of leg B is on. Then I will write 90 to 180 degrees. Top switch of leg A is on. TA plus is on. It is permanently on. ठीक है. तो ये हो गया 0 to pi. Okay, let us see what happens pi to 2 pi. तो उसके लिए मुझे ये extend करना पड़ेगा omega t, omega t, omega t, omega t. Let me draw these carrier waves again. 6 carrier cycles. 1, 2, 3, 4, 5, 6, 1, 2, 3. So this is ये 180 degrees है, तो ये 270 degrees है, तो ये 360 degrees है, या 2 pi का ही है. Okay, so I am now considering pi to 2 pi. Pi to 2 pi आप देख सकते हैं. Your MA star पहले आप ड्रा कर लीजिए. MA star आपकी ये है. MA star नीचे आएगी. Then 180 to 270 degree it is -1, and then it rises in this, goes up and it rises like this. Okay, like this. I am following this. Okay, what about MA star? MA star ऐसे है. So MA star is something like this. It is like this, and then it is clamped to positive DC bus. Okay. Yeah, I am reproducing this. Earlier I was, discussing with you positive half cycle of inverter output voltage 0 to pi. उसको मैंने दो quarters में divide किया था, 0 to 90 degrees and 90 to 180 degrees. Because 0 to 90 degrees TB minus is on. So phase leg B is clamped to negative DC bus, and 90 to 180 degrees TA plus is on, and it clamps leg A to positive DC bus. Now let us consider 180 degree to 360 degree, that's pi to 2 pi. इसको भी हम क्वार्टर में डिवाइड करेंगे 180 to 270 degrees and 270 to 360 degrees. Let us first consider 180 degrees to 270 degrees. From 180 degrees to 270 degrees, you can very clearly see, if you see MA, अगर आप MA देखेंगे, MA is -1. MA is -1 means the bottom switch of, MA is -1 means triangular carrier waves are higher in amplitude than reference or modulating wave MA. तो उसका मतलब जब carrier waves इस पूरे 90 degrees में higher amplitude में है than MA star, that means bottom switch of leg A is on. So TA minus is on, that makes pole voltage VAO all throughout equal to minus VDC by 2. तो इसकी pole voltage minus VDC by 2 हो जाएगी, minus VDC by 2. Leg A की VAO pole voltage will be minus VDC by 2, right? And what about leg B? Leg B की switching हो रही है, ये देखिए leg B की switching हो रही है. So let me draw these points of intersection. ये देखिए, this is MB star. From this period to this period, triangular carrier wave is higher in amplitude than MB star. तो leg B की switching हो रही है, and which, since triangular carrier wave is higher in amplitude than MB star, so bottom switch TB minus will be on here, and VBO will be minus VDC by 2 during this period. So it will be minus VDC by 2. So let me show you VBO. It's minus VDC by 2. And from this instant to this instant, MB star is, modulating wave is higher in amplitude than triangular carrier. The top switch of leg B is on. TB plus is on. So therefore VBO is plus VDC by 2. So it's plus VDC by 2, then it will be again minus VDC by 2, plus VDC by 2, minus VDC by plus VDC by 2, and so on. Okay, so therefore from 180 to 270 degree is quarter में 90 degree interval में leg B is switching, but leg A is not switching. It is clamped to negative DC bus. So VAO is minus VDC by 2, and VBO switches like this. Okay. So what about 270 to 360 degrees? From 270 to 360 degrees, we can see now MB star is 1. So MB star is higher in amplitude than triangular carrier waves. That means the top switch of leg B is on. When top switch of leg B is on throughout the 90 degree interval, VBO will be plus VDC. So VBO आपका plus VDC के बराबर, plus VDC by 2 के बराबर हो जाएगा. It will be plus VDC by 2. It will not switch. That means leg B is clamped to positive DC bus. It will not switch at all. But leg A is switching क्योंकि leg A की modulating wave ये है. Let me draw these points of intersection. Okay. From this interval to this interval, MA star modulating wave is higher in amplitude than triangular carrier wave. So top switch of leg A is on. So VAO is plus VDC by 2. So it is plus VDC by 2. And then from this instant to this instant, triangular carrier wave is higher in amplitude than, from this instant to this instant, triangular carrier wave is higher in amplitude than reference sine wave. So bottom switch TA minus is on. So VAO is minus VDC by 2. So it will remain minus VDC by 2 इस इंटरवल में भी. ओके, लेकिन उससे पहले मुझे यहाँ से यहाँ देखना पड़ेगा. या फ्रॉम दिस इंटरवल टू दिस इंटरवल, फ्रॉम दिस टू दिस triangular reference sine wave MB star is higher in amplitude than triangular carrier wave, and top switch TA plus is on. So it will be यहाँ से यहाँ तक ये एक और point of intersection. Your load voltage, pole voltage will be plus VDC by 2. Or from this instant to this instant, triangular carrier wave is higher in amplitude than reference sine wave. So bottom switch of leg A is on. So VAO will be equal to minus VDC by 2 from this instant to this instant. Then it will be plus VDC by 2, minus VDC by 2. Then again plus VDC by 2, minus VDC by 2, plus VDC by 2. That's all. ये 2 pi. yeah, up to this, yeah, 2 pi. What about load voltage? Now it is interesting to see the load voltage pattern. Now we know load voltage is VA minus VB, VAO minus VBO. This is my load voltage. यहाँ से यहाँ आप देखिए, your load voltage is, this is VAO minus VBO minus VDC by 2 plus VDC by 2. It is 0. Then it is minus from during this interval, it is VAO minus VBO, that's minus VDC by 2 minus VDC by 2. Minus VDC by 2 minus VDC by 2 is minus VDC. And then this minus this is again 0. Then this minus this is again minus VDC. Then during this period again 0, then minus VDC. Okay. Then this is, this minus this is again plus VDC by 2 minus VDC by 2. So it is again 0. Then minus VDC by 2 minus VDC by 2. It is again minus VDC. Then during this period is again VDC by 2 minus VDC by 2 is 0. Then during this period minus VDC by 2 minus VDC by 2 minus VDC. Then during this period again 0. During this interval again minus VDC. And that's it. So ये है 180 degrees, ये है 360 degrees. And 270 degrees is somewhere here. ये 270 degrees. Okay. Let me rub off this portion because I have reproduced this waveform here. Now let me take negative half cycle. I will take now negative half cycle of inverter output voltage. उसमें भी मैं quarter cycle पहले ले लूँगा. I will take 180 to 270 degrees. So 180 degree to 270 degree interval. इस quarter में आप देख सकते हैं MA star is -1. So bottom switch of this is on. TA minus is on. So MA star is equal to, you can see it is equal to -1, which means TA minus bottom switch is on throughout this period. It's on means it is not switching at all. This switch is not switching, it is on permanently. Okay, and what and that means phase leg A, since bottom switch is on, your pole voltage during this period, you can say it is minus VDC by 2. That is, leg A is clamped to negative DC bus. So I will write leg A is clamped to negative DC bus. And whereas, you know, leg B is switching. Leg B is switching. ये leg B है, उसकी pole voltage ये है. देखिए switch हो रही है. So I will write here leg B is switching. Leg A is not switching. It's clamped to negative DC bus, but leg B is switching. और आपकी inverter output voltage during this period, you can see it is equal to here it is 0. It is 0 when bottom switches of both the legs are on. That means TB minus तो on है ही, TA minus is also on. TA minus तो on है ही, TB minus is also on. So TA minus, TB minus both are on. Then it is equal to minus VDC. You can see it is equal to minus VDC when, see, bottom switch of leg A तो TA minus ये तो on ही रहेगा during entire 90 degree interval, और top switch of leg B is on, TB plus. When top switch of leg B is on, that's why pole voltage is plus VDC by 2. So TA minus TB plus is on. TA minus TB plus on. Now we can see from the power circuit diagram, TA minus TB plus is on. TA minus is on means A is connected to negative DC bus. TB plus is on, B is connected to positive DC bus, and load voltage is minus VDC. And then it is again equal to 0. When it is again equal to 0, then again bottom switches are on. TA minus, TB minus on. You can see TA minus is on. Conduct nahi ho raha hai, switch nahi ho raha. It's not switching because leg A is clamped to negative DC bus. Leg A is not switching. Whereas you can see leg B is switching. First TB minus is on, then TB plus is on. Then again TB minus on, then again TB plus on. So leg B is switching. तो ये हो गया from 90 to 180 degrees. Okay, 90 to 180 degrees में कौन सा switch permanently on है? TA minus permanently on है. Okay, TA minus permanently on है. I should write that somewhere. I'm writing मैं already यहाँ I'm noting down 0 to 90 degrees TB minus is on permanently, 90 to 180 degrees TA plus is on permanently, and I will write now 180 degrees to 270 degrees TA minus is on permanently. Okay, this was about 180 to 270 degrees. Let us go to last quarter of waveform, that is 270 to 360 degree interval. 270 to 360 degree interval, 270 degrees to 360 degree interval. In this interval, you can say MB star is high. It is greater in amplitude than triangular carrier wave, and MB star controls the switching of leg B. Since it is MB star is 1, so top switch TB plus is permanently on. So MB star is equal to 1 means TB plus is on. It is permanently on. It is not switching at all. It's on. That means leg B is not switching. So which means leg B is not switching. It is clamped to positive DC bus. Since upper switch on है, so leg B is clamped to positive DC bus. Positive DC bus. Whereas you can see leg A switch हो रही है. You see leg B तो it gives pole voltage plus VDC by 2. Leg B is not switching, but leg A is switching. Plus VDC by 2, minus VDC by 2, plus VDC minus 2. Leg A switch हो रही है. So I will write leg A is switching. So inverter output voltage, you can see it's either equal to 0. Let us start from here. It is equal to 0. When it is 0, you can see the top switches are on. Here TA plus is on, here TB plus is on. TB plus to on hai during entire interval, 90 degree interval. So TA plus, TB plus on. So it is equal to minus VDC. Now it is equal to minus VDC. When it is minus VDC, your pole voltage VAO is minus VDC by 2. That means bottom switch of leg A is on. TA minus or TB plus to on hai. TA minus TB plus on. So TA minus TB plus on, that means load voltage is minus VDC. And it is again equal to 0. It's again equal to 0 when top switches of both the legs are on. TA plus, TB plus on. Now you can see TA plus is on here, here, here. Sorry, TB plus is on here, here, here. So TB plus is not switching. That's already known to us. TB plus is not switching. Phase leg B is already clamped to negative positive DC bus. Leg B is not switching, but leg A is switching. You can see first TA plus is on, then TA minus is on, then again TA plus on, then again TA minus on. So leg A is switching. So therefore, which switch is permanently on for 90 degree interval during this period? TB plus is on. It is not switching. So during this interval, that is 270 degrees to 360 degrees, TB plus is on. Okay. So therefore, we have considered the entire one cycle of inverter output voltage 0 to pi, pi to 2 pi. So 0 to pi we divided into two quarters, 0 to 90 and 90 to 180 degrees. Pi to 2 pi also we divided into two quarters, 180 to 270 and 270 to 360 degrees. And we have found that in the positive half cycle of inverter output voltage 0 to pi, when we take first quarter 0 to 90 degrees, TB minus is not, it's permanently on, it's conducting, it's not switching. That is leg B is clamped to negative DC bus. So TB minus is on for 90 degrees. Whereas leg A is switching. You can say leg A is switching. And inverter output voltage is like this. From 90 to 180 degrees, we see that TA plus is 1, TA plus is on. You can see 90 to 180 degrees, TA plus is on. That is leg A is not switching, it is clamped to positive DC bus, whereas leg B is switching. Okay, and inverter output voltage is like this. In the negative half cycle of inverter output voltage, that's 180 degrees to 360 degrees. Let us take first quarter, 180 to 270 degrees. TB minus is on. I have written here, TA minus is on. TA minus is on, that means leg A is clamped to negative DC bus. It's not switching, but leg B is switching. And inverter output voltage is 0 minus VDC, 0 minus VDC like that. And 270 to 360 degrees, TB plus is on. That means this TB plus conducts for 90-degree interval. It clamps leg B to positive DC bus. It is not switching, leg B is not switching, but leg A is switching, and inverter output voltage is like this. If you find the instantaneous average value of inverter output voltage, it is sinusoidally varying like this. It will be sinusoidally varying like this. Although your reference waves, modulating waves are not sinusoidal, they are like this. Okay, and they also make instantaneous average pole voltages also will have same average value, same pattern. But as far as inverter output voltage V naught is concerned, which is VAO minus VBO, it's purely sinusoidal in nature. Okay, that I repeat, although your modulating waves are not sinusoidal in nature, they are like this, which makes average instantaneous pole voltages also to be like this. But inverter output voltage, VAB or V naught, is not following this pattern. It is purely sinusoidal. The reason being that inverter output voltage is MA star in terms of modulating signals. It is MA star minus MB star. And what is MA star? It is MA plus MCM, common mode voltage, actual modulating wave plus common mode voltage, minus what is MB star? That is also MCM plus, that is MB plus MCM, minus MB plus MCM. That case में minus है तो ये भी minus हो जाएगी. Common mode voltage cancels in the inverter output voltage. So inverter output voltage becomes finally MA minus MB. Since MA, MB actual modulating waves are sinusoidal, so that's why average instantaneous average inverter output voltage is also sinusoidal in nature. We can very clearly see. Okay, so why did we distort these modulating waves? Why didn't we let them to be sinusoidal? We distorted them for the purpose of bus clamping, because it resulted in bus clamping of both the legs. For example, 0 to 90 degrees, which leg was clamped? Leg B was clamped. It was not switching, whereas leg A was switching. 90 to 180 degrees, leg A was clamped, leg B was switching. 180 to 270 degrees, leg A was clamped again, and leg B was switching. And 270 to 360 degrees, leg B was clamped, and leg A was, it was not switching, but whereas leg A was switching. So therefore we can very clearly see that since if you see leg A is clamped from 90 to 180 degrees, and it is clamped to positive DC bus, of course, and it is clamped to negative DC bus from 180 to 270 degrees. So that means from 90 to 180 degrees and 180 to 270 degrees, which is total 180 degrees. 180 degree में leg A स्विच ही नहीं हो रही है, तो इसमें स्विचिंग पावर लॉसेस हाफ हो रहे हैं. सिमिलरली लेग बी की जहां बात करते हैं, लेग बी इज क्लैम्प्ड from 0 to 90 degrees to negative DC bus, and 270 to 360 degrees to positive DC bus. So 90 plus 90 means 180 degrees. That means leg A is also clamped to 180 degrees. Since both legs, this leg as well as this leg, they are clamped either to positive DC bus or to negative DC bus, and they do not switch for 180 degrees. Leg A switches for 90 plus 90, 180 degrees, and leg B switches for 90 plus 90, 180 degrees, whereas leg A is clamped for 90 plus 90, 180 degrees, and leg B is also clamped 90 plus 90, 180 degrees. That means each leg switches for only 180 degrees and is clamped to positive or negative DC bus for rest of the 180 degrees. Since each leg of the inverter switches only out of one cycle of 360 degree, each leg switches only for 180 degrees, half the cycle. So switching power losses are reduced by half. Switching power losses are halved, half ho jati hai, they are reduced by half. And that's a great advantage. So when switching power losses are reduced by half, inverter output, inverter efficiency, conversion efficiency will increase. And simultaneously, this type of bus clamping technique gives equal loading of all the devices, because you can see TA plus is on, it's conducting for 90 degrees. TA minus is also conducting for 90 degrees. TB plus is conducting for 90 degrees. TB minus is also conducting for 90 degrees. So all the four switches are equally loaded. This is conducting, it's on for 90 degrees. This is also on for 90 degrees. This is also on for 90 degrees. This is also on for different 90 degrees. All the four devices are conducting for 90 degrees each, which gives equal loading of the device, whereas the bus clamping was achieved in the previous technique also, जहाँ पे हमारी reference waves ऐसी नहीं थी, हमारी reference wave कुछ ऐसी थी और हमारी common mode voltage ऐसी थी, second harmonic wave, and that also resulted in bus clamping and reduced the switching power losses, but that resulted in conduction of only top switches TA plus and TV plus. Bottom switches were not conducting, they were not clamping to the DC bus. So that was unequal device loading. Here, all the 4 switches you can see, they are equally loaded for 90 degrees each. So this is DC, this bus clamping technique with equal device loading. Therefore, we can say that bus clamping technique with this equal device loading we achieved by adding even harmonics. So addition of even harmonics, the type of common mode voltage that we added, if you analyze it, it will have second harmonic, fourth harmonic component, sixth harmonic component, eighth. It will not have odd harmonic. So it is even harmonic wave. It modified our modulating reference waves or modulating waves, and it gave bus clamping. The results in bus clamping with equal device loading. All the 4 devices or IGBTs of the inverter were equally loaded, and inverter output voltage did not get affected. Inverter output voltage or load voltage does not get affected. It remains sinusoidal. Instantaneous average value is sinusoidal, because common mode voltage subtracts when you calculate the inverter output voltage. Okay, so that is therefore the advantage of adding even harmonics, modifying your modulating or reference wave, is to go for bus clamping, reducing the switching power losses of the inverter, but simultaneously with equal device loading. That's how we have achieved it today. And simultaneously, inverter output voltage does not get affected. So with this, I will end this lecture. So that completes our discussions on inverter, bus clamping technique, even harmonic injection, and hence bus clamping technique with unequal device loading as well as with equal device loading over the last 2 lectures for single phase PWM voltage source inverters. Inshallah, from our next lecture, we will start discussions on 3-phase PWM voltage source inverters. Please go through this lecture and stay connected. Thank you.